Hello everyone, and today in this introduction to remote sensing course, this is 12th lecture. We will be talking about how remote sensing can be integrated with the other two powerful technologies, GIS, that is Geographic Information System, and global navigation systems. One of the example is GPS, but we will be discussing also some other navigation systems as well. As you know that in earlier lectures also I have mentioned that GIS, GPS and remote sensing are having three common things in between. That they are generic technologies, that means they can be applied to various areas, application areas, and there are few areas still unexplored. So in future we will be seeing the applications of these technologies either in an integrated fashion or maybe individually or maybe two technologies together. Maybe in some more new technologies may come in between, but the three common things are generic, so that they can be applied for various applications, spatial, which are related with the location specific data, because remote sensing images provides the data of a particular part of the earth. So it is having location. Same in your GPS, GPS provides the geographic coordinates, and GIS provides a platform to handle all kinds of spatial data. Therefore, these technologies we put them as spatial technologies as well. And finally, the third common thing between these technologies is digital. Digital means originally the remote sensing data is collected in digital form, transmitted in digital form, and now there are digital platforms, computer or image processing softwares are available, so we can digitally process the data, interpret the data and analyze the data according to our requirements. Same with the GPS. GPS data is also available in a digital format, and GIS again the platform which provides to handle all kinds of remote sensing and GPS data. So these three commonalities between these three technologies have allowed us to create new types of applications, new types of products. One of the very popular product which nowadays we are using is like Google Map or Google Earth, which are using remote sensing technologies like Google Earth, as well as digital elevation model, which has been derived from remote sensing data, and it's a custom designed GIS software. And if you are having GPS input collected from some location, field surveys, especially for civil engineers, then that too can be put on that one on Google Earth. So it's a wonderful product which is an integrated product of GIS and remote sensing, plus you can add your input data from GPS as well during field surveys. As you know that GIS, because GIS has not been introduced in this course, but there is a separate course which I have delivered on GIS, but just for completeness I thought that I will bring the just definition of GIS, which is a computer based information system designed to accept large volumes of spatial data. Spatial data means location specific data, objects which are having geographic locations, and that data might be coming from variety of sources, and the purpose of GIS platforms are to efficiently store that spatial data, retrieve it as per user requirements, analyze it and model it, so that we can analyze to that extent that we start predicting about some phenomena, some features, or for exploration purpose or any other purposes. So model and then finally display or create outputs as per user defined specifications. So that's the purpose of GIS, which allows us to handle all kinds of spatial data on a digital platform. The data might be coming from variety of sources. It also allows you to convert analog data into digital data to some extent in a semi-automatic manner, and then you finally integrate everything and start creating new products. The important point here that these are the few terms we use interchangeably. sometimes synonymously, but in fact if we start looking in details, we will find that these are all together different words, different terms have got different meanings. For example, data and versus information. The data is basically about the raw facts. Data is nothing but a raw facts by itself generally differs from the information. And suppose somebody has got the data about some surveys which has been done in the field and just fed in the say Excel sheet. Now till then it will remain the data. No analysis has been done, no other processing has been done. But once I start doing some analysis, simple maybe statistical analysis, maybe some sorting thing. Suppose somebody has gone in the field, collected water sample data. Now if he has collected 30 samples from different areas, then I want to see the distribution. So I will try to plot the map on a GIS platform in a form of map using geographic coordinates, and this will start giving me the clustering information and other things, whether the data has been collected uniformly or collected from only in a small area and so on and so forth. Plus also that what is the highest value, the data which I have collected, what is the lowest value. Suppose value I talk about pH. So where is the pH highest in the water and where is the less. So once you start analyzing these things on the raw facts, that is the data, then your data is converted to information. But before that, just collecting the data from the field and putting into say Excel sheet or database doesn't become that information. It has to be analyzed. Certain kind of operations, analytical operations, statistical operations have to be performed on that, and once these are done, then this data can be converted into information. So these are two terms. This should be taken completely differently. Data, as I mentioned, that data is itself little use unless it is transformed into information, and today's the computer technology is allowing us to transform these raw facts, the data, into information quite easily. And information is an answer to a question based on raw data. We create questions. Once the data has been analyzed, it is converted to information. Now when we raise the questions, for example, I can raise that where I have found the minimum pH value in the water samples, where I have found the maximum pH value, what is the average pH value, or in which areas, if I have plotted these locations, then in which area I am getting higher pH value, in which area less. So all kinds of questions, once the data has been converted to information, can be answered. Various types of questions, may not be all kinds of questions. So but the GIS goes one step forward. It converts your data in not only into information but also into the knowledge, that we will see here now. That first is the raw facts or data. Using computers we can convert this into the information, but when we use the GIS platform along with some other informations, maybe remote sensing data or maybe some other maps, maybe soil map or a elevation map or some other thing, then I can convert that into the knowledge, and this becomes a very powerful. That is why GIS becomes a very powerful tool, so that the raw data by itself analysis and further processing can directly be converted into knowledge, and that makes a lot of utility of GIS. Otherwise, simply using computers, maximum you can do, you can convert into information, but using GIS you can convert to knowledge. Now the third technology, this is GPS. As we know that GPS was invented in the early 90s, or well, it came in the civilian domain in the early 90s when there were war between Kuwait and Iraq, and the American army entered in that war from the Kuwait side. And what happened then, they started, because they were doing this or they were having war in a desert area and landmarks are very difficult to find. So using just simple topographic sheets, it was very difficult. So by that, but before that they developed this technology mainly for army purposes, and that was the navigation system, and they gave this name global positioning system. Earlier it used to be called like strategic defense initiative or it was a part of Star Wars of Ronald Reagan. Parallelly also, when the Americans were developing GPS, which is now known as GPS, parallelly Russians were also developing, and that system is called GLONASS. And that both systems are global navigation systems. But GPS came first, and it was allowed by to use by the civilians, and therefore it became very popular. And still today, even in our mobiles, we are having GPS receivers, handheld GPS receivers, and much more advanced versions of like differential GPS are available today. And in civil engineering, especially in surveying, extensively these things are being used. So basically, if we look the definition of GPS or any navigation system, basically it's a network of orbiting satellites that sends precise details of their position in space back to Earth. And these signals are obtained by GPS receivers such as navigation devices and are used to calculate the exact position, speed, time at the vehicle location. The concept wise is simple. If you look the earlier surveying methods, we used to, if we wanted to know where I am located on a map, then what we used to do, we used to take back bearing during our field surveys from two known points which I can see from my naked eyes in the field itself, and the same corresponding points I can also locate in my topo sheet. So then we used to take back bearing from these known 2 points which I am seeing, and at the same time I am seeing in topo sheet, and then drawing these lines. So wherever these lines used to cut, we used to say that we are located here. In order to make certain that we are there exactly where we have just seen through these two crossings of two back bearing lines, then we used to take back bearing from third point. And if third point also, the back bearing line, if also cuts at the same point where two lines earlier have cut, then we are very much sure that we are on this particular location. This concept of back bearing was on 2D. This concept with the satellite technology, especially with navigation systems, it became a 3D technology. So here what basically happening, that there is a constellation of satellites which we will see which system is having what type of constellation, and then these satellites are at in each orbit there are, say if I take the example of GPS, then there are six satellites are there, 6 orbit are there, and in each orbit you are having 4 satellites, and all these are having they are having in each orbit, they are having at equal distance. Each satellite is having its unique ID. So what each satellite is doing, also they are having synchronized atomic clock. So what they are doing, they are sending the signals which is a time stamped, date stamped, location stamped signal, and saying that I am in space at this location and I am dispatching this signal at this moment. So when a receiver receives this signal, I know that how much time it has taken, because there is a time which is when signal was sent from there, it is there, and so the time taken by that signal to reach to the receiver gives me the distance if I multiply by the speed of light. And why, as like in concept of back bearing, if I start getting signals by my receiver from 3 such navigation satellites, then I would know where exactly on globe my receiver is. So in back bearing, minimum back bearing readings were only 2 required, but it's a 3D, so minimum 3 are required to know X and Y position, that is latitude and longitude. But if I want to know the height or elevation of a point where receiver is kept, then I need to have one more signal from one more satellite, and that is the 4th, and that will give you the 3D. So 3 satellite will give you 2D, 4 satellite will give you 3D. We will see all these things in little detail as well, that how GPS works. That GPS devices tells you where are you, and by calculating the exact distance from 4 GPS satellites at a given time. The first one, there are these figures keeps changing because there are some spare satellite. In case of this US GPS, American GPS or navigation system, which we call as GPS, a minimum constellation is the 24 satellites in 6 orbital planes. 6 orbital planes are there, and so that at a time minimum, if you are in an open area, you should be able to get at least signals from 6 to 8 satellites at a time minimum. And then these satellites continuously transmit their precise location. Every second they are sending a pulse, a signal from there towards the earth, that I am here, at this moment I am dispatching. Let me give you an analogy. Like if I post a letter from Roorkee to say Chennai. So when I leave this letter into the letter box, then in the post office it is stamped that it is being posted from Roorkee on this date and this time. When it reaches to Chennai, then again that post office will stamp. So by looking these two stamps, I can estimate that how much time it has taken to reach from Roorkee to Chennai. Almost similar concept, that it is in digital form, that signal once it received, the distance is calculated and direction is known, so that these ranges, basically these are the ranges, as you are seeing in this animation, that as person keeps moving, that he is getting the location, because the 4 satellites are continuously communicating with his GPS receiver, and that location is being calculated every second for that person or for that receiver. So the GPS receivers pick up the satellite signals which are being transmitted by all these 24 satellites all the time, every second, and determine our location by triangulation method. So this is how this, what is that triangulation? That is working out our location based on intersecting area between all the GPS satellites and the GPS receiver which are communicating with them. Now think that if I am on the mountain, on a hilltop, then I would be able to get maybe even signals from 10 satellites. And if I am say on Mount Everest, probably I might be able to get signals from 12 satellites, because then hindrances are less. So if I want to have a good position, then I need to have a very large open sky. If I am in a valley, then I might be getting very less signals from less number of satellites. The signal quality might be also good, not good, and therefore my position estimations might not be also good. Nowadays when we use in our smart mobile the Google map, when we switch on, initially it will show a large blue circle, and after some time you would realize that that blue circle has become a very small blue circle. So what is basically indicating? That now initially the error margin was much larger. That means the estimation was very poor, but once it starts getting the signals from various satellites, GPS satellites, then my position has improved, position estimations have improved, and therefore the error circle, which is blue, has reduced. And so that sometimes by using some other application programs, you can know that what kind of accuracy you are getting. So we go on further on this, how GPS works. Basically, as I have been saying, that these like in case of towers, mobile towers, how they get the concept of a GPS, how they get this signal, that each tower, if each tower keep transmitting its location as well, apart from signals, then wherever these the range of these towers, that means these circles, 3 circles will cut, that is the position where I am standing. This is how a GPS works. Think that instead of 2D, means on a plane area, on a surface of the earth, if I consider these as spheres, and instead of towers I consider them as satellites, in the same way when these 3 spheres will cut, that would be going to be my position of my receiver. So this triangulation location or triangulation concept is, here it is in 2D, but in case of satellite it becomes a 3D. So satellite 1 is, whenever this range is available, I know now the radius of my a sphere. So one satellite will give the one sphere, another satellite once I start getting signal, I find the distance between receiver and satellite, then the another sphere will come. Now then there will be the 3 sphere. Suppose I am getting signals minimum from the 3 satellites. So wherever these all 3 satellites will cut, the spheres will cut. In circles it is looking only 1 point, but in case of spheres there will be 2 points. So one would be very far from surface of the earth. Therefore, the other point which is close to the surface of the earth is going to be location of the receiver. So the 3 satellites together provide the exact location of the receiver. And now as I mentioned that each satellite broadcasts radio signals with their location, status and precise time information. This is very important to note that each satellite every second is sending signals, and these are in the radio frequencies, and that means that in all weather conditions, day and night, 24 hours, we can receive signals from the constellation of one navigation system. For example, here a GPS, which is American one, and once the time is calculated, the dispatch time, receiving time, then distance is available. Now one sphere for this satellite, one sphere for this, one sphere for this, and one sphere. And likewise GPS radio signals travels at a speed of this 300,000 kilometer per hour, and GPS receiver device receives radio signals noting their exact time of arrival and uses these to calculate the distance from each satellite. Basically the distance, once distance becomes available, then this imaginary sphere which I am emphasizing can be calculated or can be drawn by the receiver itself, or calculations about or estimations about position can be done. So once a GPS receiver knows its distance from at least 4 satellites, it uses the geometry to determine its exact location of the earth in 3D. If I am only interested in 2D, then 3 satellites, minimum 3 satellites are sufficient. But if I want to know not only X and Y but elevation as well, then I need to have the signals at least from 4 satellites. As I have mentioned that when US was developing their Navistar system, that is the GPS or Navistar satellites, and that is GPS, the same time the Russians were also developing a system which is called GLONASS. Later on some regional systems have also come, which is the European countries have also developed Galileo, Baidu. India has also developed, I will discuss little later. But why there are requirements? Once a global navigation system became available in somewhere in 1990s, earlier it was accuracy part was not as good as today, but at least it was there and it was globally available to anyone who is having appropriate receiver. So why other countries started developing? Because if we start depending everything on the GPS for all kinds of navigations, whether for aircraft operations or for taxi fleet operations or for the railway engines operations, then it would have been a complete monopoly of US. And then whenever they wanted, they could have switched off and all our navigation system would have gone completely haywire. So in order to not to depend completely on American navigation system, that is GPS, Russians also developed. Basically it was originally Navistar or GPS was developed to for the missile technology, but it became much more popular equally in our day-to-day life. Then GLONASS was again it is also a global navigation system, and even in nowadays in not very expensive smart mobiles, their receivers are capable, GPS receivers are capable of receiving signals from Navistar, that is USGS, GPS, as well as from GLONASS. So if instead of getting from one navigation system, signals from one navigation system, it is possible to receive signals from many navigation systems. And so now these receivers, small tiny receivers, are coming with smart mobiles or handheld GPS receivers that they can receive signals from various navigation systems. So Russians also developed parallel to the American system, and almost same time the third system came, as I mentioned, by the European countries, that is the Galileo. But Galileo is not truly a global system. Galileo is a regional system. Then Chinese also came, because they too never wanted to depend themselves on GPS, that is Navistar or GLONASS. So they too came with their own navigation system. Design wise, constellation wise, it is completely different than typical GPS system or GLONASS system. This Baidu navigation system of China is having altogether different constellation. Same time also, when India realized that we need to also develop our own system, not only for missile technology, but also for day-to-day life in the civilian world, for all kinds of navigation. So we went with this kind of, initially it used to call IRNSS, and then later on it was renamed as NAVIC. And they say, though it has not become fully operational, but I am sure that very soon our mobiles will have a receiver which might be receiving signals not only from GPS, that is Navistar, Galileo, and Baidu, because Baidu also provides it's a global navigation system. It also provides data free of cost, and maybe if I am using such receivers in India, I might be also getting signals from NAVIC as well. If I get even in a valley, if I get signals from 10-15 satellites of different navigation system, definitely my position estimations are going to be very accurate if I compare just, or if I get signals only from one navigation system. So that is the advantage for us going to be, that if we start getting signals from many navigation systems of the world, then our position estimations are going to be very accurate. Generally we get with the simple these smart mobiles, we get say position estimation, this error margin may be 5 meter or 10 meter sometimes, but if I am getting signals from 3, 4, 5 navigation systems, that accuracy might be improved even within 1 meter, which is a very good for many applications. Now this whole I have so far introduced very briefly what is GIS, also very briefly about the GPS, and remote sensing we have been anyway discussing. So now this main purpose of this lecture was to have this how to integrate all these technologies so that we get a very nice product. So there are different models which we can think, that is, one is the interactive model of integration, which is very popular, very commonly used. As I have said, that all the data which is either remote sensing data or data from coming from GPS or your GIS platform, they all handle the geographic data, that is means spatial data, and that is the advantage. So the coordinates basically, or like if you are having a satellite image, after doing georeferencing or rectifications, image rectification, you get the coordinates for the image and satellite image. So that becomes your georeference satellite image, and this is two-way, because sometimes a standard a georeference image can also be used to georeference another image which is not yet in geographic domain. It might be in geometric domain or may not be yet georeferenced. So that is why it is two-way. Nowadays for let me give you an analogy, like nowadays for very high resolution satellite images, if we want to do it georeferencing, that means we want to convert from geographic coordinate to geometric coordinate to geographic coordinate, then we are also using coordinates and for GCPs, our ground control points, using even Google Earth. So a registered or georeferenced satellite image can also become a master image for another image which is not yet georeferenced. So, that is why it is in two direction. Same way, once I have got the georeference data, satellite images, then I get the database construction on a GIS platform which will provide not only the satellite data information, the outputs from the satellite data information and data images, but also data from other like digital elevation models, maybe a soil map, maybe a land use map, maybe a forest cover map, and so on and so forth. Because GIS is capable of handling all kinds of information, especially the spatial information on a digital platform. And then I might perform some kind of modeling on a GIS platform that can go again back to my satellite images to see, like people are doing nowadays, that whatever the product they are creating on a GIS platform after doing all kinds of analysis on satellite images and along with other data sets, they put directly on Google Earth and then see that how it fits there with the surroundings. So, that is why this is another arrow is there, that once I have done the modeling, I can put again on the Google Earth and see things along with the surroundings, as well as I can transmit to some others who can also see once they double click on the Google Earth. So, that is the advantage. So, it is a interactive model of data integration, and this concept is given here. Then there is another model we can think of, which is a hierarchical model of data integration, that we are having coordinates. Coordinates might be coming from survey topo-sheets, coordinates might be coming from GPS, or coordinates might come from standard products like Google Earth, Google Map. So, they go here for my data georeferencing of satellite images, and again for overlaying with the other maps on a GIS platform. I might be having a GIS database separately, which is again georeference having geographic coordinates, and then I can integrate, again do the modeling and can create some products. Modeling here means, suppose I am working for for landslide hazard zonation. So, for that purpose I need lot of information, not only about the slope, but the land use and road network, maybe some geological structures, faults and other things. So, all these things once I am available, I may assign certain weights, or I may employ some known models for that particular area and can create a map, an output, a model which will show that where, if these conditions remain like this, then where the slope will fail first, and which are the slopes which are most vulnerable, and next and next. So, that is basically modeling, predicting about the future. The third type of integration model is the complex model. So, rather than having interactive or hierarchical model, a complex model of integration can also be thought here, that again the coordinates, the spatial information becomes the key. So, coordinates are there, overlays are there on a GIS platform, and then you may have to have a database construction, in situ data collection, that means going in the field, collecting the data, collecting the samples, analyzing the sample, putting into the database, coming into GIS, and then again creating such models, environmental model or any other model, like maybe soil erosion model or some other models, maybe putting on a GIS satellite images. Today I am suppose I have used the satellite images of 2010. Now I have also seen in 2015. Now what would happen after 5 years? I may project, I may model, and then when 2020 comes, I would be able to see that how accurate my model was, because the satellite images can provide the time series data. So, all these things are possible to do it, even if one goes for complex model of data integration. So, all kinds of models are being implemented to integrate data, especially on GIS platform, data coming from satellite images, data coming from GPS, data coming from variety of sources, that is the spatial data and field data, survey data, and all these are going on a GIS platform, and then you create a final product, a model, a prediction and other as per user defined. So, what is the possibilities of the future integration possibilities with RSGIS and GPS? Just is a thought, may not things may work little differently, because we may have more powerful, more useful images, more powerful GIS technology, more better GPS signals or navigation signals. Maybe some new technology might be coming, but if we think that whatever the technologies which are present, then how these things will be integrated, that what we are going to see an increased number of remote sensing platforms, that is more number of remote sensing satellites, leading for more accurate and regular data, higher spatial resolution data, higher radiometric resolution data, higher temporal resolution data, and on regular basis. That is one very real possibility. Then the current era, that is times to come, and most likely continues to emphasize visualization of information. Because as you remember in other previous lectures, I have mentioned that a picture tells 10,000, a picture tells 1,000 words, whereas a map or a model can, especially a map, can tell 10,000 words. So this visualization, a satellite image will give you more information than a simple picture, and if it is a GIS product, then it may give you much more information even than a simple satellite image. So that kind of emphasis on visualization will continue. Remote sensing images will be the key input for all kinds of analysis, and of course GIS is going to be powerful and more user friendly, so that a person who does not have much knowledge of computer science programming can also use GIS very easily. So this is what the future navigation data coming from variety of systems, 4-5 systems I have discussed, one more from Japanese side are also available. So all these might get in only one receiver. So it means in near future we might be having a receiver which is going to be a kind of a universal receiver. So it can receive signals from all types of navigation systems, whichever are presently or in future. Such a open system might come, a universal system might come, and our accuracy estimations will improve, say to just few centimeters, as nowadays we are. It is possible only through differential GPS, but not with simple GPS navigation system. So that is the geospatial accuracy definitely is improving. It is going to improve very soon on this front. And the last one here is that the user interfaces to continue become much more standardized and user friendly. So all these technologies are going to become user friendly in near future. So this brings to end of this special topic of discussion. Thank you very much.